Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Inside an engine compartment, near a furnace door, around an industrial oven, or inside an electrical enclosure, one small material is often standing between safe operation and catastrophic failure: the sealant. It looks simple: a gray-black or red paste squeezed from a cartridge. But chemically, it is an engineered network designed to survive heat, vibration, oil, moisture, oxidation, and mechanical movement. Today we are exploring a powerful question: what is the difference between silicones and silanes, and how do chemical engineers use both to manufacture high-temperature industrial sealants? Silicones form the flexible, heat-resistant body of the sealant. Silanes act like molecular bridges, helping the sealant bond to metals, glass, ceramic, fillers, and industrial surfaces. This is the chemistry behind the seal that survives where ordinary polymers fail. The story begins with silicon chemistry. In the early 20th century, chemists were studying compounds containing silicon, oxygen, carbon, and hydrogen. Frederick Stanley Kipping helped establish the foundation of silicone chemistry and gave these materials the name silicones. At first, silicones were laboratory curiosities. But the world changed when Eugene Rochow developed a practical route to methylchlorosilanes around 1940. This industrial route opened the door to large-scale silicone production. Soon, silicone materials entered aerospace, electrical insulation, automotive engines, construction joints, medical devices, and industrial sealing. Why did industry need them? Because many organic rubbers become hard, brittle, or oxidized at high temperatures. Silicone chemistry offered something different: a silicon-oxygen backbone with organic side groups, producing a material that stayed flexible across a wide temperature range. The names sound similar, but they are not the same. A silicone is usually a polymer. Its backbone is made of repeating silicon-oxygen units, COCO. Organic groups like methyl groups are attached to the silicon atoms. This gives flexibility, low surface energy, weather resistance, and thermal stability. A silane, in sealant technology, is usually a small reactive molecule. A common form is XRC, or 3-1 end can react with an organic polymer. The other end can hydrolyze and bond to inorganic surfaces like glass, silica, metal oxides, ceramics, and fillers. So, silicones build the rubber body. Silanes build the chemical bridge. Most common organic rubbers rely mainly on carbon-carbon backbones. These materials can be strong and useful, but at high temperature they can oxidize, harden, crack, or lose elasticity. Silicone rubber is different because its backbone contains alternating silicon and oxygen atoms. The CO backbone gives silicones excellent heat resistance and low-temperature flexibility. The organic side groups shield the backbone and help control surface properties. This is why silicone sealants are used in engine gaskets, furnace access doors, electrical enclosures, industrial ovens, turbocharger systems, LED assemblies, aerospace components, and high-temperature appliances. But there is an important point: silicone does not mean unlimited heat resistance. A typical industrial high-temperature silicone sealant may work around 250 degrees Celsius continuously, and some specially formulated grades may handle around 300 degrees Celsius or slightly above for limited exposure. Above that, decomposition, loss of elasticity, and filler changes must be considered. A high-temperature industrial sealant is not just one chemical. It is a carefully balanced formulation. A typical formulation may contain base polymer, hydroxyl terminated or functional silicone polymer, reinforcing filler, fumed silica or treated silica for strength and thixotropy, extending filler, calcium carbonate, quartz, alumina, or other mineral fillers, thermal stabilizer, iron oxide, cerium compounds, or other heat-resistant additives, depending on product design, crosslinker, acetoxy, alkoxy, oxim, or other silane-based curing agents, catalyst, tin, titanium, platinum, or other catalyst systems depending on cure chemistry. Adhesion promoter, organofunctional silane. Pigment, red iron oxide, black carbon, gray mineral pigment, or custom color. Plasticizer or silicone fluid, for extrusion, flexibility, and workability. Every ingredient must be controlled. Too much filler, and the sealant becomes stiff. Too little filler, and it loses strength. Too much catalyst, and shelf life collapses. Too little catalyst, and curing becomes slow. Many industrial silicone sealants are called RTV silicones. RTV means room temperature vulcanizing. In simple words, the material is applied as a paste, then cures into an elastic rubber at room temperature. There are two major industrial families. RTV1, one-component system. It cures when moisture from air diffuses into the sealant. It is packed in a moisture-tight cartridge or tube. RTV2, two-component system. Two parts are mixed before application. Cure starts after mixing, and it can be faster and deeper than moisture cure systems. For formed in-place gaskets, flange sealing, oven joints, and field repair, RTV1 is popular because it is easy to use. For automated potting, electronics, large volume casting, or thick section curing, RTV2 can be preferred. The magic happens through hydrolysis and condensation. In a moisture cure silicone sealant, the polymer chains have reactive end groups. The crosslinker contains hydrolyzable groups. When atmospheric moisture enters, these groups hydrolyze and form silanol groups. A simplified reaction is C or plus H2OC, OH plus ROH, then condensation links the chains, COH plus HO, CCOC plus H2O. Gradually, a three-dimensional silicone network forms. The paste becomes rubber. This is why humidity, bead thickness, temperature, and joint design affect curing speed. The outside cures first. The center cures later. If the bead is too thick, moisture may take a long time to reach the core. Not all RTV sealants cure the same way. Acetoxy cure silicones release acetic acid during cure. They often have a vinegar-like smell. They cure well and are widely used, but acetic acid can corrode some metals or affect sensitive electronics. Neutral cure silicones release less corrosive byproducts, depending on the chemistry. They are preferred for electronics, sensitive metals, and many industrial assemblies. Alkoxy cure silicones release alcohols during cure and are often used where low odor and neutral cure are important. Oxim cure silicones release oxim-type byproducts and have also been widely used in industrial sealants, though safety and regulatory considerations depend on the exact chemistry. Choosing the cure system is not just chemistry. It affects odor, corrosion, adhesion, shelf life, cure speed, compatibility, and worker safety. Now let us focus on silanes. Imagine trying to bond rubber to glass or metal. The rubber is organic and flexible. The surface is inorganic, hard, and often covered with hydroxyl groups or oxide layers. Without help, the interface can fail. A silane coupling agent solves this problem. One side of the silane reacts with inorganic surfaces such as glass, silica, metal oxides, and mineral fillers. The other side interacts or reacts with the polymer system. This creates a molecular bridge, surface OCR polymer. The bridge improves adhesion, water resistance, filler dispersion, and long-term durability. This is why silanes are used as adhesion promoters, primers, crosslinkers, filler treatments, and surface modifiers. Even the best sealant can fail if the surface is dirty. Industrial surfaces may contain oil, oxide dust, machining fluid, moisture, rust, paint residue, or release agents. These contaminants block chemical bonding. A proper sealing process often includes degreasing with approved solvent, abrasion or roughening if required, plasma, corona, or flame treatment for difficult low-energy surfaces, application of primer when needed, controlled drying time before sealant application. This is where silane primers become important. A primer can deposit reactive silane chemistry onto a difficult surface, turning a weak interface into a durable bond. In chemical engineering terms, adhesion is not only a material property. It is a process property. Manufacturing a high-temperature silicone sealant begins before mixing. It begins with moisture control. Remember, RTV1 sealants cure when they contact moisture. That means moisture is useful during application, but dangerous during manufacturing and storage. Raw silicone polymer, fillers, crosslinkers, catalysts, and adhesion promoters must be stored carefully. Fillers may be dried. Tanks and mixers may be blanketed with dry nitrogen. Packaging must prevent moisture ingress. If moisture enters too early, the sealant can partially cure in the mixer or cartridge. This causes lumps, poor extrusion, short shelf life, and batch rejection. So the first rule of RTV manufacturing is simple: keep moisture out until the customer applies the product. Fillers are not just cheap solids. They control strength, viscosity, thixotropy, thermal stability, color, and cost. Fumed silica creates reinforcement. It increases strength and prevents the sealant from sagging on vertical surfaces. Mineral fillers reduce cost and modify thermal expansion. Iron oxide can help in high-temperature red gasket sealants. But fillers can carry moisture. They can also have surfaces that interact strongly with the polymer, sometimes making the paste too thick. Chemical engineers may use treated fillers, silane-treated surfaces, or controlled mixing sequences to obtain the right rheology. Good filler dispersion is critical. Poor dispersion creates weak points, rough extrusion, poor mechanical properties, and inconsistent cure. The heart of the plant is the mixer. High-viscosity silicone sealants are commonly mixed in planetary mixers, sigma blade mixers, or double planetary vacuum mixers. The polymer and fillers are blended under controlled temperature and high shear. Vacuum is applied to remove trapped air. Without vacuum, air bubbles can remain inside the paste. In a sealant bead, those bubbles become leak paths, weak spots, or cosmetic defects. Mixing is a balance. Too little mixing gives poor dispersion. Too much mixing generates heat, damages thixotropy, or shortens pot life. Engineers monitor torque, temperature, vacuum level, mixing time, and batch viscosity. In this stage, the sealant begins to look like a paste, but it is not yet complete. The most sensitive stage is the addition of reactive ingredients. Crosslinkers, catalysts, and silane adhesion promoters are often added after the main filler dispersion. This reduces premature reaction and protects shelf life. The crosslinker decides how chains will connect. The catalyst decides how fast the cure will happen. The silane promoter decides how well the sealant will bond to the surface. This stage is performed under low moisture, controlled temperature, and precise dosing. Even small errors can change cure speed, tack-free time, extrusion force, skin formation, and final adhesion. In chemical manufacturing, a sealant is not mixed by guess. It is built through sequence, timing, and process control. After mixing, the sealant goes through deaeration and sometimes filtration or screening. The goal is simple: remove air, remove lumps, and deliver a uniform paste. Then the material is filled into aluminum tubes, plastic cartridges, sausages, drums, or automated dispensing containers. For RTV1 products, packaging must be moisture-tight. The nozzle and cartridge seal become part of shelf-life engineering. If the package leaks moisture, the product may skin inside the cartridge. If the filler dispersion is poor, the nozzle may clog. If viscosity is too high, the user cannot apply it. If viscosity is too low, the bead sags. Every detail matters from reactor to cartridge. A high-temperature sealant must pass quality tests before shipment. Common tests include appearance and color, density or specific gravity, extrusion rate, viscosity and slump resistance, tack-free time, cure through depth, hardness, often Shore A, tensile strength and elongation, adhesion to metal, glass, ceramic, or customer substrate, heat aging at defined temperature, compression set for gasket applications, shelf life stability. For high-temperature sealants, heat aging is critical. Samples may be exposed to elevated temperature, then tested for cracking, hardness change, weight loss, tensile retention, elongation retention, and adhesion loss. A sealant is not qualified by appearance alone. It must prove performance. Now let us compare their roles inside the final sealant. The silicone polymer forms the elastic network. It gives flexibility, thermal resistance, weatherability, and sealing ability. The silane chemistry does three important jobs. First, silane crosslinkers help convert paste into rubber. Second, silane adhesion promoters bond the sealant to substrates. Third, silane-treated fillers improve dispersion and mechanical performance. So the comparison is not which is better. The correct question is, what job does each molecule perform? Silicone is the body. Silane is the connector. The sealant succeeds when both are engineered correctly. High-temperature silicone sealants are used wherever heat, movement, and sealing must exist together. In automotive engineering, they are used for formed-in-place gaskets, engine covers, oil pans, thermostat housings, and exhaust-adjacent components, depending on grade. In electrical and electronics industries, neutral-cure silicones protect assemblies from moisture, vibration, thermal cycling, and dust. In furnaces, ovens, boilers, and industrial dryers, sealants help close gaps and joints that expand and contract with temperature. In aerospace and defense, specialized grades may be used for bonding, sealing, vibration damping, and environmental protection. But selection must always consider actual service. Temperature, exposure time, oil or chemical contact, movement, substrate type, and cure conditions. When a sealant fails, the material is often blamed. But in many cases, the failure is caused by wrong selection or wrong application. Common failure modes include adhesive failure, the sealant separates from the surface. Cohesive failure, the sealant tears inside itself. Thermal cracking, excessive temperature damages the rubber. Oil swelling or softening, chemical exposure exceeds compatibility. Poor cure, moisture could not reach the center, or catalyst was inhibited. Bubble leakage, air remained in the bead. Sagging, viscosity and thixotropy were not suitable. Corrosion, wrong cure chemistry used on sensitive metal. Primer failure, surface was dirty or primer was not dried correctly. This is why high-temperature sealing is both material science and process engineering. Silicones and silanes are often confused, but in industrial sealant manufacturing they play different and complementary roles. Silicones provide the heat-resistant, flexible, rubbery network. Their silicon-oxygen backbone allows performance across a wide temperature range, making them valuable for gaskets, engines, electronics, ovens, and industrial equipment. Silanes provide the chemistry of connection. They help bond polymer to metal, glass, ceramics, fillers, and mineral surfaces. They improve adhesion, moisture resistance, and durability. The final sealant is created through controlled formulation, dry processing, filler dispersion, vacuum mixing, precise catalyst addition, moisture-tight packaging, and strict quality control. So next time you see a bead of red or black sealant on a hot engine or industrial furnace, remember, it is not just paste. It is polymer chemistry, surface science, heat transfer, rheology, process engineering, and quality control, all packed into one cartridge.